Welcome to the Deep Dive. Today we're tackling a real cornerstone of organic chemistry. Clayden, Greaves, and Warren's Organic Chemistry, this second edition. Specifically, Chapter 17, all about elimination reactions.
Yeah, right, a fundamental chapter.
And our mission today is really to get inside the head of these molecules, figure out their decision-making process. How do they choose to shed atoms, form new bonds, and maybe more importantly, how can we as chemists sort of nudge that choice?
Exactly. It's all about control.
We'll be looking at the mechanisms, the how and why, functional group changes, the whole stereochemistry puzzle, and even how this fits into planning out a synthesis.
Yeah, understanding eliminations is just, well, it's essential if you're doing any kind of synthesis. We'll try to boil down the key ideas from the chapter, keep it clear for audio, but without losing the important details. You'll get a sense of the factors involved, subtle electronic things, big steric effects. And it's cool, the authors even point you to interactive 3D models online at www.chemtube3d.com/Clayden. You just type the page number after that. Really helpful for visualizing.
Oh, nice resource.
Yeah.
Okay, let's dive in. We've talked before about substitution reactions, SN1 for instance.
Yeah.
Tertiary alkyl halide, leaving group pops off. Rate doesn't care about the nucleophile. Simple enough.
Right?
But what if you take that same scenario or something similar, and instead of a mild nucleophile, you hit it with something really strong, like, say, concentrated sodium hydroxide? Does it just speed up the substitution?
Well, often no. That's where things get interesting. The reaction pathway can actually change completely. Instead of substitution, you often end up forming an alkene.
An alkene? How?
Well, overall, you lose the elements of, say, HBr from the starting material. We call that an elimination. And the key thing is that strong nucleophile, the hydroxide in your example, starts acting predominantly as a base.
A base instead of a nucleophile.
Right. Exactly. Instead of attacking the carbon atom where the leaving group is, it plucks off a proton, a hydrogen atom, from the carbon next door. It's a fundamental shift in reactivity.
Okay, so the region choice dictates substitute versus eliminate. But like substitution, I guess the eliminations aren't all the same either. There must be different ways this can happen, different mechanisms.
Absolutely. Just like SN1 and SN2, we have main mechanisms for elimination. We'll focus on the big two, E2 and E1.
E2 and E1.
E2 stands for elimination bimolecular. Think of this one as perfectly synchronized. It's a concerted reaction.
Concerted, meaning everything happens at once.
Precisely. The base grabs the proton, and at the very same time, the leaving group, like bromide, takes off, and the double bond forms, all in one step.
Wow.
And because two things, the alkyl halide and the base, have to collide in that crucial step, the rate depends on the concentration of both. The classic example is tert-butyl bromide reacting with concentrated hydroxide. That often goes E2.
A synchronized dance. I like that.
Yeah.
So E2 is bimolecular and concerted. E1 must be different.
Very different. E1 is elimination unimolecular. This one's a two-step process. Step 1, the leaving group leaves, all by itself.
Like in SN1.
Exactly like SN1. It forms a carbocation intermediate. That's the slow step, the rate-determining step. Then, in a second, usually much faster step, something acts as a base, often a weak base, maybe even the solvent, and removes the proton from the carbon next to the carbocation.
Okay, so leaving group leaves first, then proton removal.
Right. And because that first slow step only involved the alkyl halide molecule falling apart, the overall rate depends only on the alkyl halide concentration. The base concentration doesn't directly affect the rate of that first step.
Makes sense. Any classic examples of E1?
A good one is heating tert-butanol, which is an alcohol, in strong acid like sulfuric acid. The acid protonates the AOH, making it a great leaving group, water. Water leaves, forms the tert-butyl cation, and then the weak conjugate base, HSO4, or even another water molecule, pulls off a proton to give the alkene.
Okay, that distinction between E1 and E2 is clear, but it brings up that big question. How does the molecule, or rather, how do we decide which path it takes? When does a nucleophile act as a base and cause elimination? What pushes it one way or the other?
That's the million-dollar question in synthesis design, right? There are really three main factors you need to consider. First, and maybe most obviously, is the basicity of the nucleophile.
Stronger base means more likely to eliminate.
Exactly. Strong bases are just better at pulling off protons. Think about ethanol, ETOH. It's a weak base, usually favors substitution, but its conjugate base, the ethoxide ion, ETO, that's a strong base. And that strongly favors E2 elimination.
Okay, basicity check. What's next?
The second factor is the size of the nucleophile or base. How bulky is it?
Sterics. That always comes up.
It really does. See, for substitution, the nucleophile has to get in close to attack the carbon atom. If that carbon is crowded or if the nucleophile itself is big and bulky, that attack is difficult.
Harder to squeeze in.
Right. But pulling off a proton from an adjacent carbon, those protons are usually sticking out on the periphery of the molecule, much more exposed. So a big, bulky base finds it much easier to just grab a proton than to try and force its way in for substitution.
So bulky bases favor elimination.
Strongly favor E2 elimination, yes. The classic example is potassium tert butoxide, KOT-BU. That tert butyl group is huge. It's an excellent choice when you want elimination and want to avoid substitution, even with primary alkyl halides where substitution might otherwise compete.
Clever. Use the bulkiness to steer the reaction. Okay, basicity, size. What's the third factor?
Temperature. Higher temperatures generally favor elimination over substitution.
Why is that? Is it just making everything go faster?
It's a bit more subtle. It comes down to entropy. Think about what's happening. In a typical elimination, you start with, say, 2 molecules, the alkyl halide and the base. You end up with 3 molecules, the alkene, the leaving group ion, and the protonated base.
Okay, 2 becomes 3.
Right. In substitution, you usually start with 2 and end with 2. So elimination reactions typically involve an increase in the number of molecules, which means an increase in disorder or entropy.
And entropy likes higher temperatures.
Exactly. Remember the Gibbs free energy equation, LiDo-G equals teeth. That negative teeth term becomes more significant, more negative at higher T if aqueous is positive. This makes T more negative, meaning the reaction is more favorable. So cranking up the heat often tips the balance towards elimination. Most eliminations are run at room temp or hotter.
Fascinating. Basicity, size, temperature. 3 key levers to pull. Now, going back to the mechanisms, E1 needs that carbocation. E2 is concerted. How does the actual structure of the starting material, the substrate, influence which one happens?
Hugely important. For E1, as we said, you need a stable carbocation intermediate. That means tertiary alkyl halides are great candidates, allylic and benzylic ones too, because the charge can be delocalized.
Right, resonance stabilization.
Exactly. Secondary alkyl halides might go E1 under the right conditions, usually with very weak bases and high temperatures, but primary alkyl halides, never E1. A primary carbocation is just too high in energy, too unstable to form readily.
Got it. No stabilization, no E1.
We also mentioned alcohols with acid, like cyclohexanol going to cyclohexene with phosphoric acid. That's a common E1 route. The acid protonates the OH, turns it into water, a fantastic leaving group, which then leaves to form the secondary carbocation before proton loss.
You mentioned something earlier about rigid structures, basic ones.
Ah, yes. Bread rule. It's a really neat structural constraint. In some bicyclic systems, the carbon at the bridgehead where the rings fuse simply cannot become planar, which is what's needed for a carbocation's sp2 hybridization.
Too much strain.
Way too much ring stream. So if the leaving group is on a bridgehead carbon that can't flatten out, E1 elimination is effectively forbidden there. The carbocation just can't form.
Wow. Okay, what about E2? Is it less picky about the substrate?
E2 is generally more flexible. It can happen with primary, secondary, and tertiary alkyl halides. The main requirement is a strong base.
Like the bulky TBO we mentioned.
Yep, TBOK is a classic. Another really useful one mentioned in the book is DBU.
DBO.
1008 diazabicyclo 5.4.0 undecene 7. It's a mouthful, but it's a strong, non-nucleophilic hindered base. Great for promoting E2 without causing substitution side reactions. Its structure makes it basic, but also bulky.
Okay. And the leaving group itself. Obviously important for E1 because it has to leave on its own. How critical is it for E2?
Still very critical. A good leaving group makes both E1 and E2 faster, but there's a key difference with alcohols. We said protonated alcohol leaving as water is great for E1 and acid,
Right.
but for E2 reactions are run in base. You can't have an alcohol leaving as hydroxide, OH. Hydroxide is a terrible leaving group, and the strong base would just deprotonate the alcohol anyway.
So you can't do E2 directly on an alcohol?
Not usually on primary or secondary ones. What you do is convert that OH group into something else that is a good leaving group under basic conditions. You essentially give it an upgrade.
How do you do that?
A common strategy is to turn it into a sulfonate ester, like a tosylate, using TSCl, tosyl chloride, or a mesylate, using MSCl, mesyl chloride. These raw Ts, or ROMs groups, are fantastic leaving groups, kind of like bromide, but derived from an alcohol. Then you hit it with your strong base, like TBO or DBU, and you get clean E2 elimination.
Ah, so a two-step process. Activate the alcohol, then eliminate.
Exactly. Activate, then eliminate.
Okay, this is where it gets really, really interesting for synthesis. controlling where the double bond forms and its geometry. Can we actually dictate that? Like get
Yeah.
specifically the E or the Z alkene or the double bond on one side versus another?
Yes, absolutely. This is where understanding the nuances pays off. Let's talk stereoselectivity first, favoring one stereoisomer, like EVSC.
Okay.
E1 reactions tend to be stereoselective. They usually favor the E alkene, the one where the larger groups are on opposite sides of the double bond, trans.
YE.
Mostly sterics again. The E alkene is generally more stable because there's less crowding between the large groups. The transition state leading to it is also lower in energy. Clayden gives an example where you might get 95% E and only 5% E from an E1 reaction.
So E1 gives a preference, usually for E. What about E2? Is it just selective or something more?
E2 is often stereospecific. That's a stronger word. It means the stereochemistry of the starting material directly determines the stereochemistry of the product. There's no choice or preference, it's locked in by the mechanism.
Wow. Why is E2 so specific?
It comes back to that concerted mechanism and the requirement for an anti-paraplanar geometry in the transition state. The CH bond being broken and the C leaving group bond have to be aligned, parallel but pointing opposite ways 180 degrees apart.
That specific alignment is necessary.
Absolutely necessary for the orbital overlap that allows the electrons from the CH bond to flow in and push out the leaving group while forming the pi bond. If that alignment can't be achieved, the E2 reaction is much slower or it doesn't happen at all. Can you give an example of where this really matters?
Cyclohexanes are the classic case study. For an E2 reaction on a cyclohexane ring, both the proton being removed and the leaving group must be in axial positions to achieve that anti-paraplanar arrangement.
Both axial.
Both axial. So if you have two diastereomers, say, one where the leaving group is axial and an adjacent proton is axial, and another where maybe the leaving group is equatorial, or the only adjacent protons are equatorial, they will react via E2 at vastly different rates. Or one might not react at all via E2. It directly proves the geometrical requirement.
That is incredibly specific. So the starting molecule's 3D shape dictates the outcome rigidly for E2.
Precisely. It's also key when making alkenes from vinyl halides via E2. The elimination is much faster if the proton and the halide are trans across the double bond, again, because that's the anti-paraplanar setup.
Okay, that covers the easy geometry aspect.
Mhm.
What about where the double bond forms if there's a choice? Say you could form it between C1, C2, or C2, C3. That's regioselectivity, right?
Yeah. Exactly. Regioselectivity. Where does the region of reactivity, the double bond, end up?
How does that play out for E1?
E1 reactions generally follow Zaitsev's rule, sometimes spelled Zaitsev. They tend to form the more substituted alkene as the major product.
More substituted is more stable.
Generally, yes. More alkyl groups attached to the double bond carbons means more stability, usually due to hyperconjugation. Since E1 goes via a carbocation and is often under thermodynamic control, it prefers to form the most stable possible alkene product.
Makes sense. Path of least resistance leads to the most stable place. What about E2 regioselectivity? Does it always follow Zaitsev too?
E2 is where we get more control. It can follow Zaitsev's rule, especially with small, strong bases like ethoxide. But if you use a bulky, sterically hindered base, like our friend potassium tert-butoxide,
Let me guess, it changes the outcome.
it often flips the outcome. A bulky base has trouble reaching the more sterically hindered protons that would lead to the Zaitsev product, the more substituted alkene. Instead, it preferentially attacks the most accessible, least hindered proton,
Which
usually leads to the less substituted alkene. This is often called the Hofmann product. So by choosing your base, small versus bulky, you can often direct the E2 elimination to give either the more substituted Zaitsev or the less substituted Hofmann alkene.
That's real synthetic power, choosing the base to choose the product location.
It absolutely is. It's not just about rules like Zaitsev and Hofmann. It's understanding the Y sterics accessibility of the proton.
Okay, we've covered E1, E2 factors, stereochemistry, regioselectivity. But there was one more mechanism mentioned in the chapter outline, E1CB. What's the deal with that one? Sounds a bit unusual.
It is unusual. E1CB stands for elimination unimolecular conjugate base. It's different because the order of events is flipped compared to E1 and E2.
Flipped how?
In E1CB, the first step is deprotonation. The base removes the proton to form a carbanion intermediate the conjugate base of the starting material. Then, in a second, unimolecular step, the leaving group gets kicked out from this carbanion intermediate to form the alkene.
Deprotonation first. But wouldn't that require a really acidic proton?
Exactly. That's the key requirement for E1CB. You need an electron withdrawing group, something that can stabilize the negative charge of that carbanion intermediate.
Yeah.
A carbonyl group, CO, is a classic example. If you have a carbonyl next to the CH bond you're breaking, it makes that proton acidic enough for a base to remove it first.
And the leaving group just waits until the anion forms.
Pretty much. The anion forms, and then it pushes out the leaving group. And here's a fascinating twist. Remember we said hydroxide is a terrible leaving group and never leaves an E2?
Yeah.
Well, in certain E1CB reactions, OH can actually be the leaving group, especially if the anion is well stabilized and the alkene product is conjugated, like with that carbonyl group. The formation of the stable conjugated system provides enough driving force.
Whoa, a rule breaker mechanism.
Yeah.
Where do we actually see this E1CB pathway?
It pops up in specific situations. Formation of conjugated systems like unsaturated carbonyl compounds from halocarbonyls is one area. The book also mentions some really interesting hidden E1CB examples. Yeah, like during the synthesis of penicillin V. Apparently, an agyryl chloride intermediate with an acidic alpha proton undergoes an E1CB elimination to form a superreactive species called a ketene. That ketene then reacts further.
A ketene. CCO.
Right, that's the one. Highly reactive. Another example is when you make mesylates using mesyl chloride, MsCl. A side reaction can occur where MsCl undergoes an E1CB elimination of HCl to form an intermediate called a sulfene, the sulfur analog of a ketene.
So these reactive intermediates can form via E1CB. Is the rate law weird too?
It can be. Even though the leaving group departure is unimolecular, the 1 in E1CB, the overall rate often does depend on the base concentration. Why? Because the concentration of that crucial carbanion intermediate depends directly on how much base you have to form in the first place, so it's kinetically a bit complex.
Okay, E1, E2, E1CB. Quite the tour of elimination chemistry. So stepping back, what are the big takeaways from this deep dive into Chapter 17?
I think the biggest takeaway is how much control we can have and how reactions are governed by this really delicate balance of factors. Substrate structure, the nature of the base, its strength, its size, and temperature, they all interplay. We've seen how these factors dictate the mechanism, E1 or E2, or maybe even E1CB.
And the mechanism dictates the outcome.
Exactly. It dictates the stereochemistry, whether you get E or Z or whether it's specific. And it dictates the regiochemistry, whether you get the more or less substituted alkene. Understanding these connections is just fundamental for making molecules intentionally. Eliminations are everywhere, from making simple alkenes to complex pharmaceuticals like tamoxifen, or even forming those reactive ketenes and sulfenes.
It really is amazing how subtle changes in conditions can lead down completely different molecular roads. Thinking about all this, the mechanisms, the steric effects, the stereospecificity, how does it change the way you might look at a reaction on paper or plan a new synthesis? What stands out most to you?
For me, it's probably the stereospecificity of E2 and the control offered by bulky bases and regioselectivity. They're such powerful tools when you're trying to build something complex with specific geometry.
Powerful tools indeed. Well, we hope this deep dive into Chapter 17 of Clayden, Greaves, and Warren has given you some valuable insights, maybe a few aha moments about how these eliminations really work. Thank you for being part of the Last Minute Lecture family.